Hi everyone. In the last lecture, we discussed spectral theorem and a few examples to illustrate the spectral theorem. Today, we are going to discuss one more important application of the spectral theorem. Namely, we want to look at polynomials of self-adjoint operators. Okay. So let us quickly recall. So if let T be a self-adjoint operator, then we have shown that there exists a family of projections E lambda, where lambda in R, such that T can be written as integral a to b lambda dE lambda, where a is less than the lower numerical bound and b is bigger than or equal to the upper numerical bound. And we have seen the meaning of this is nothing but T can be approximated by Riemann sums of the form summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1, where lambda not equal to a less than lambda 1 less than or equal to lambda 2, so on lambda n equal to b. This is a partition of AB, and this lambda j hat is a point in lambda j minus 1 lambda j equal to 1 to n. Okay, now we want to ask what will happen to t square. You know t, so let us the question is the following: how to represent t square. Then we can ask later that how to represent t power n for a natural number. So let us look at this. So now t is limit of summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1. So we can say that this implies t square is the limit of summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1 square. So let us look at what will happen to this square. So consider E lambda j minus E lambda j minus 1 square. This is E lambda j minus E lambda j minus 1 multiplied by E lambda j minus E lambda j minus 1. So this is nothing but this is E lambda j square this is E lambda j square, but E lambda j square is E lambda j. So let me write minus E lambda j minus 1 minus E lambda j minus 1 E lambda j plus E lambda j minus 1 E lambda j minus 1. Now each E lambda j is a projection, so we can write this is E lambda j square j, and the last term is E lambda j minus 1. Now let us look at these two terms. Now lambda j minus 1 less than lambda j, So the product of two such operators is the least projection we get. So this is the first one is E lambda j minus 1, and here also E lambda j minus 1. So we will get E lambda j minus E lambda j minus 1. Now E lambda j and E lambda j are orthogonal projection, hence they are self-adjoint. So note that this is E lambda j minus E lambda j minus 1. That means E lambda j minus E lambda j minus 1 is an orthogonal projection. Now if you look at so hence we can actually say that summation j equal to 1 to n lambda j into E lambda j minus E lambda j minus 1. If I look at square of this, you will get this summation j equal to 1 to n lambda j square E lambda j minus E lambda j minus 1. This is what we get. That means t square can be approximated by this kind of operator, summation j equal to 1 to n lambda j hat square multiplied by E lambda j minus E lambda j minus 1. But this represents integral a to b lambda square d E lambda. So let us start with some epsilon positive. Let epsilon be given. Now, so as the representation of t is this integral a to b lambda d E lambda. So there exists a delta such that if p equal to lambda naught, that is a, less than lambda 1 less than lambda 2, this is less than lambda n equal to b, be any partition of AB with norm of p, that is maximum of lambda j minus lambda j minus 1, if this is less than delta, and if you take any lambda j hat inside this jth subinterval, so we have that norm of t minus summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1 norm less than epsilon. So here instead of epsilon we can take this is less than epsilon by norm of t into b minus a. So this we will understand why we have to take this one at a later stage. So let us call this as inequality 1. Okay, so let us write a as summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1. So we are looking at norm t square minus a square. This we can write as norm t plus a into norm t minus a. So this is less than or equal to norm t plus norm a into norm t minus a, and norm a is less than or equal to summation j equal to 1 to n mod lambda j hat into norm of E lambda j minus E lambda j minus 1. So that is an orthogonal question that will have value 1, and summation j equal to 1 to n mod lambda j, that is less than or equal to length of the interval. So on the whole you will get it is less than or equal to b minus a. So this is less than or equal to norm t plus b minus a multiplied by norm t minus so. So here we have to take epsilon by norm t plus b minus a. Okay, now we can say that this is less than, so norm t minus a less than norm t is less than epsilon by norm t plus b minus a, so this is less than epsilon by 1. But so that means we know that norm t square, now a square we have already computed, that equal to summation j equal to 1 to n lambda j hat square e lambda j minus e lambda j minus 1, that is less than epsilon. So this implies t square can be written as integral a to b lambda square d lambda. Yeah, okay, so we actually forgot one more step. So before yeah, let us look at here. If you look at e lambda j minus e lambda j minus 1 whole square, now if you look at square of this one, summation j equal to 1 to n lambda j hat e lambda j minus e lambda j minus 1 whole square, that contains terms of the form e lambda j minus e lambda j minus 1 whole square and terms of the form e lambda j minus e lambda j minus 1 into e lambda I minus e lambda I minus 1. So let us look at that part. So this is proof is completed provided this condition is also verified. So e lambda j minus e lambda j minus 1 into e lambda I minus e lambda I minus 1. So let us take ij in n with I less than j. Then let us look at this mixed terms, because we also get mixed terms in this square you will get mixed terms of the form e lambda j minus e lambda j minus 1 multiplied by e lambda I minus e lambda I minus 1. So hence we can say that this is e lambda j e lambda I minus e lambda j e lambda I minus 1 minus e lambda j minus 1 e lambda I plus e lambda j minus 1 e lambda I minus 1. So when I less than j, we will get this as e lambda I. When I is strictly less than j, I minus 1 is strictly less than j or less than or equal to j, so we will get e lambda I minus 1. Here also when I less than j, I less than or equal to j minus 1, so here we will get e lambda I, and the last one is, so I minus 1 is less than or equal to j minus 1, so we can say this is e lambda I minus 1, so you will get this is 0. That means the mixed term cancels here and homogeneous terms remain, and they are actually orthogonal projections. So now we can say that okay, so now from this we can say that a square is exactly summation j equal to 1 to n lambda j hat square into e lambda j minus e lambda j minus 1. So from this we can actually, remaining proof is as it is. So this completes the proof of representation of t square. Okay, now we can ask the same question, what will happen to t power 3, t power 4, all those things. So we can actually prove the same way. So I will write as a corollary. Instead I write a generalization. T equal to T star be a bounded operator on H, and E lambda be the spectral family generated by T. Then we have T power k is integral a to b lambda power k d lambda. Here a less than the lower numerical bound and b is bigger than or equal to the upper numerical bound. And in fact, still we can generalize this. If p is a real polynomial, on AB, that means the variable is coming from this interval, then we can show that P of T is self-adjoint and integral a to b P lambda d lambda. So the proof is similar to the earlier one. Here what we have to do is look at norm of P of T minus P of summation j equal to 1 to n lambda j hat e lambda j minus 1. So this you will get as norm of P of T minus, using the same calculation that we have done earlier, you will get P lambda j hat multiplied by E lambda j minus E lambda j minus 1. Okay, now from this we can actually get an estimate. To make this, we can actually show that this is less than or equal to epsilon, provided norm of T minus summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1 is less than some suitable constant epsilon by something. Okay, so from this we can actually get the conclusion. Okay, so one more important application with this result is, now P of T is a self-adjoint operator. This can be easily shown by the definition, because if P of T is a0 plus a1t plus an t power n, where these ai's are real numbers I equal to 0 to 0, 1 to so on n, and an is non-zero. Now t is a real variable. Now from this we can easily show that P of T is star equal to P of T, that is P of T is self-adjoint. Now we want to find the norm of P of T. So we have norm of P of T, it's a self-adjoint operator, that is equal to spectral radius of P of T. That is nothing but supreme of P of lambda mod P of lambda. Lambda is coming from, okay, so this is P of mod mu, where mu is coming from spectrum of P of T. Now this we can write as mod mu can be written as mod P of lambda, where lambda is coming from spectrum of T. So this is a spectral mapping theorem. P of spectrum of T is spectrum of P of T. Okay, now supreme of mod P lambda, lambda is coming from spectrum of T, is less than or equal to supreme of mod P of T, where T is coming from the interval closed interval a comma b, because the closed interval a b contains spectrum of T. So this is nothing but sup norm of So we can say that operator norm of P of t less than or equal to supremum norm of P. Okay. So these are some of the important applications of the spectral theorem. Here we give one more important application of the spectral theorem. Let P be a real polynomial and T is a self-adjoint operator. Then we can say that P of t is positive if and only if P is positive on spectrum of t. Okay, so the proof follows from the earlier result that when t is self-adjoint, P of t is self-adjoint. So we have P of t star is P of t. We know that a self-adjoint operator is positive if and only if the spectrum is positive. So we have P of t is positive if and only if spectrum of P of t is contained in the positive real line. Now we know that spectrum of P of t is nothing but P of spectrum of t by the spectral mapping theorem. So this is by the spectral mapping theorem. So that means P takes positive values on spectrum of t. So this is nothing but P equal to 0 on spectrum of t. Okay, so this is another application. Now let us look at one more important application. We can actually represent self-adjoint operator using vectors also. Let T be a self-adjoint operator which is bounded, and E lambda is coming from R, be the spectral family generated by T. Then we can say that for every x, y and h, so we can write inner product Tx with y is nothing but integral a to b lambda d lambda inner product x with y, d lambda x, d e lambda x inner product with y. This is for every x, y and h. Okay, so now we have to understand what is the meaning of this expression. Okay, so here to show that representation of Tx with y, inner product Tx with y, it is enough to look at inner product Tx with x and apply the polarization identity. So let us write, so enough to show inner product Tx with x as integral a to b lambda d e lambda x inner product with x. Now let us look at the map alpha lambda equal to inner product e lambda x with x, where x is fixed. So let us fix x and look at this map lambda in R. Now this alpha lambda is an increasing map in lambda. Now we can actually give a meaning for this integral a to b lambda d e lambda x inner product with x. So that is nothing but we want to show that inner product Tx with x is integral a to b lambda d alpha lambda. This alpha lambda is an increasing function So we can, this is nothing but Riemann-Stieltjes integral. Inner product Tx with x is nothing but Riemann-Stieltjes integral. So let us look at the proof. Let us take epsilon to be positive. Then there exists a delta such that if P is any partition like this, is any partition of with norm less than or equal to delta, and let us take any arbitrary point lambda j in the jth subinterval. Then it follows that norm of P minus summation j equal to 1 to n lambda j hat e lambda j minus e lambda j minus 1. This norm is less than epsilon. But we want to look at inner product Tx with x and the corresponding Riemann-Stieltjes sum with respect to the increasing function alpha lambda. So we have here, it is modulus inner product Tx with x minus summation j equal to 1 to n lambda j hat e lambda j minus e lambda j minus y inner product x with x. Now this is less than or equal to norm of T minus summation j equal to 1 to n lambda j hat e lambda j minus e lambda j minus 1 into norm x square. So we have fixed norm x. Now this is less than epsilon into norm x square. So we can actually show take this to be epsilon by norm x square, because x is fixed. Then we can actually make this less than epsilon. So from this we can say that inner product Tx with x is integral a to b lambda d lambda x inner product with x. Now apply the polarization identity. So by the polarization identity we can show that we can say that inner product Tx with y is integral a to b lambda d lambda x inner product with y. Now here lambda going to inner product e lambda x with y is not a real valued function, it is complex valued function. Okay, so this is the proof of the representation of T. So this representation of T is known as a weak representation of T. Okay, so I'll stop here. Thank you very much.